Question 10. Which of these pieces of apparatus has the lowest percentage uncertainty in the measurement shown? So let's have a look. We've got a volume of 25 centimetre cube being measured out on a burette. Remember, a burette, you take a reading at the start and the end, so you take two readings. Each reading has a uncertainty of plus or minus 0.1 centimetre cubed. So you take 0.1, which is the error, you multiply by the number of readings, which is 2, because two readings, each with a 0.1 centimetre cubed uncertainty, could then have an uncertainty of twice that value, 0.2. So you take the 0.1, you multiply by 2, because there's two readings. You divide by the volume that you're measuring out, and you multiply by 100. So it's the error divided by the volume, or the measurement that you're taking, multiplied by the 100. So 0.1 times 2 divided by 25 multiplied by 100%. So let's have a look at the next one, a measuring cylinder. Well, you only measure once on a measuring cylinder, and there's an error of 0.5 divided by the volume, which is 25. So it's 0.5 multiplied by 1 multiplied by 100% divided by 25. 0.15 grams measured out with a balance. Again, you only measure once on a balance with an uncertainty of 0.001. So it's 0.001 multiplied by 1 multiplied by 100% divided by 0.15. Temperature change, so this time we've got a temperature change 23.2. Now there's a temperature change, so that implies that you're measuring the temperature at the start and at the end and working out the change. So you can be measuring the temperature with a thermometer twice. So it's 0.1 multiplied by 2, because you're taking two readings, multiplied by 100% divided by 23.2. And the lowest value is the top one. The answer is A. A student is provided with 5 centimetre cube sample of 1 times 10 to the minus 2 mole to the decimetre cubed hydrochloric acid. Right, I've got a volume and I've got a concentration, so immediately I know what I'm going to have to do. I'm going to work out number of moles. Concentration is number of moles divided by volume in decimetre cubed, so 1 times 10 to the minus 2 is number of moles divided by this. I've got to get this 5 centimetre cubed divided by 1,000 though, so it's 0.005. So concentration is 1 times 10 to the minus 2 divided by, 1 times 10 to the minus 2, which the concentration is moles divided by 0.005. Number of moles is 0.005 multiplied by the concentration. Multiply these two numbers together, divided by 1,000, equals the number of moles. I'm going to have to do that first. Okay, so 0.01, which is my moles of hydrochloric acid, equals the moles divided by 0.005. Moles of these two multiplied together, 0.00005. That's the number of moles of hydrochloric acid that I've got. Now I'm going to have to work out how much water I'm going to have to add to get the concentration to be 5 times 10 to the minus 4. So I'm changing the concentration by adding water. So the new concentration is 5 times 10 to the minus 4, or 0.0005. Equals the number of moles, because the number of moles haven't changed from the first bit. I'm only about to add some water. The number of moles of hydrochloric acid has stayed the same, 0.00005 divided by volume. So the new concentration equals the number of moles that I've worked out divided by the volume. The volume is 0.0005 divided by 0.005, 0.1. Now that's in decimetre cubed. To get decimetre cubed down into a lower unit value of centimetre cubed, I multiply by 1,000, 100 centimetre cubed. So I've got to get the volume to be 100 centimetre cubed. I've already got 5 centimetre cubed of water in there, or 5 centimetre cubed of solution. I've got to get the new volume to be 100 centimetre cubed. Therefore, I'm going to have to add a further 95 centimetre cubed. So they've put 100 centimetre cubed in there to try and fool you. It's 95 centimetre cubed because you've already got 5 centimetre cubed and you've got to make it up to 100 centimetre cubed. Which of these species has a trigonal planar structure? Well, let's work it out. Phosphorus is in group 5, so it's got 5 electrons in its outer shell, 3 hydrogens, 3 bonding pairs. That leaves 3 of the electrons are bonded. Out of the 5, there's 2 left over, or 1 lone pair. So there's 1 lone pair and 3 bonded pairs. It would be you'd try and put it in a tetrahedral shape, because there's 4 there's a total of 4 bonded pairs add lone pairs. So when you have lone pairs add bonded pairs together and it equals 3, then it's going to be planar. Anything more than 3, it's going to be 4. So you've got 1 lone pair and 3 bonded pairs. 1 add 3 is 4, so it's not going to be planar. That's usually the case for most species, apart from something like xenon tetrafluoride. So it's not planar. Okay, so that one's wrong. Let's try and work out what it is. If it's got 1 lone pair and 3 bonded pairs, you'd expect it to go into tetrahedral, but it's not tetrahedral because you don't see the lone pair. So it's not 109.5, that would be something like CH4, which would be tetrahedral. It's only got 3 bonded pairs and 1 lone pair, so you don't see the lone pair, you see the 3 bonded pairs, and the bond angle comes down from 109.5. Every lone pair you put on there onto a tetrahedral shape, then it lowers the bond angle by 2.5. So 109.5 take away 2.5 is 107, and you'll see the 3 bonding pairs in a trigonal pyramid shape. Okay. BCl3 has 3 bonded pairs and no lone pairs because it's in group 3, so it's got 3 bonded pairs, no lone pair. Now that might be planar. So 3 bonded pairs, no lone pairs will repel and repel equally to give a bond angle 120 in a trigonal planar shape. So your answer is B. Let's just check through C and D. C, oxygen has got 6 electrons in its outer shell. It's lost 1 because it's come plus, so it's got 5, 3 bonded pairs, 1 lone pair. Again, it's going to be the same shape as pH3 and CH3 minus. C is in group 4, gain 1 electron, so got 5, 3 bonded pairs, 5 electrons, 2 remaining as a lone pair is 3 bonded pairs and 1 lone pair. So you've got a trigonal pyramid in A, C and D, but because BCl3 hasn't got a lone pair of electrons, that's going to be your planar shape.